In the previous sections, we were working with the law of sines. 7.1 was just straight up called the law of sines. 7.2 is that ambiguous case, the side-side angle case where you had to check for potentially two triangles. All of that was because you were given particular starting points within the triangle. So for a lot of these, you were given a pair, like a big A and a big B or a little b, or a very easy way to find a big A or a little b, so that you had a pair of angle and side to do the law of sines. However, there's now an option where you use the law of cosines. This is going to happen when there is no pairs and one angle. Because previously we had some examples where there was no pairs, but we knew two of the angles, so we just quickly found the third and then we had a pair. This is not going to be that easy because we have no pairs and one or none of the angles. The law of cosines is sometimes called the generalization of Pythagorean theorem. So like, what's Pythagorean theorem, y'all? Yeah, a squared plus b squared equal to c squared, where c squared was the hypotenuse. The problem was Pythagorean theorem only works for a perfect right triangle, like a 90-degree angle in one of the angles. So you have a hypotenuse, an adjacent and an opposite side, two legs and a hypotenuse. That is very restrictive with the types of triangles that can use Pythagorean theorem. So we developed this law of cosines that will work with any triangle. It doesn't have to be a 90-degree angle. In which case, the c value doesn't mean that it is the hypotenuse anymore. Just like before, we're labeling our triangles ABC and the sides little a, little b, little c. However you've drawn it will tell you which of these formulas you're using. The main thing I want you to take away here is, do you notice that when little a is what we're equal to, big A is what we've used, little b, little c, big C. In the meantime, we do not use that letter ever again. So notice, if you're finding little a, you will obviously use big A. Is little a used any other time? No. In this one where it's solved for b squared, is b used any other time? No. And same for c. So according to the law of cosines, the square of a side of a triangle is equal to the sum of the squares of the other two sides minus twice the product of the other two sides and the cosine of the included angle. Meaning, whatever you're looking for, you need that angle, and then don't use that side length again. So it's the other side lengths. Speaking of side lengths, let's put a little annotation on here that these are the sides and these are the angles. This is going to be very helpful for us later when we're maybe not solving necessarily for a side length. Setting up the formula is pretty much as hard as it gets because once it's set up, we're going to solve for C equals or A equals or B equals, and we're going to throw it in a calculator and get an answer. So let's see, applying the law of cosines. A surveyor wishes to find the distance between two inaccessible points, A and B, on the opposite sides of a lake. So she's standing here, and she can measure this distance. She can measure the angle that she had to turn to then measure this distance. What she wants to know is how far across the lake those 2 points are. And she can't walk over there and then swim across the lake. Okay, so this is called surveying. This is a type of engineering. She finds that B is equal to 259 meters. A is equal to 423. And the angle ACB, angle C, is 132 degrees 40 minutes. We're going to find the distance C. Now, since we're finding the distance C, we are going to use the version of the law of cosines that is solved for C equals. Sort of. It's C squared equals, but you get what I'm saying. Which means we need the following information. We need A, we need B, we need big C. Is that the information we were given? Were we given little a, little b, and big C? Fabulous. That means we can plug things into this formula and solve for C. Now I'm going to do two things at once here because otherwise you're writing things down multiple times. I'm going to go ahead and square root the entire equation. Why would I do that? To get rid of this squared on C. I'm solving for C, so I want to square root both sides. The A value here is 423, so 423 squared. plus the b value, which is 259 squared, minus 2 times a times b, multiplied by the cosine of c. Now we need to know the cosine of c. I wrote too big. Oops. And the cosine of c is currently 132 degrees, 40 minutes. That's not how I should write it in this formula, though, yeah? What should I do with the 132 degrees, 40 minutes? 132 plus 40 over 60 and leave it as a fraction. So if I did that in my calculator, I would get 398 over 3 degrees. 398 over 3. That's hard to read. Let me try to write that better. That's clearer. Good job, me. Okay, look, there are no more letters left. This is a one-stop shop in your calculator. Press second squared to get the square root, and you're typing everything in with that number of parentheses that we're using. So it is a lengthy type in, but we're typing it in. I'll give you some time. It should be a decimal. Yes, it needs to make sure you're in degree mode since we use degrees. We should get 628.1008 meters. It doesn't tell us how to round on these problems, so just please make sure you're looking like whatever the homework is asking you to round for each problem. That is a classic error for us this year, is our rounding errors. I'll highlight that in green. Or box it in green. Okay, so do we see it's just a formula that we're plugging stuff in? It now unlocks our ability to do different triangles that we were not able to solve previously. So example 2, it gave you a whole page because we write big. You don't necessarily need the whole page, so you can write relatively large if you on this problem. But it says, to solve the triangle ABC, if big A is 42.3 degrees, little b is 12.9 meters, and little c is 15.4 meters. That feels like a lot of gibberish until we see it on a triangle. So let's go ahead and draw ourselves a triangle. Ooh, thank you. Appreciate that. So here's going to be A, here's going to be B, here's C. I know that A is 42.3 degrees. Little b is 12.9 meters. Little c is, not right there, Miss Quigley, is 15.4 meters. And solving the triangle means I'm going to find all 3 missing things. What things are missing?
Big B, big C, and little a.
Very good. Big B, big C, and little a. Since we have no pairs, no big A, little a, we have only one angle, so we can't use the angle sum theorem. We know that this one, since it's side angle side, is going to make us use the law of cosines. Now, the thing that we can find is the equation version that has only one thing missing. For this problem, that means I'm finding little a first. Why would I want to find little a first? True. What do I have that would be helpful for finding little a specifically? I heard someone say degree. I have angle A. So if I find angle side length B, I can then use them as a pair, and we go back to using the law of sines. We want to try to make the pairs because objectively, law of sines is easier. It's just a cute little proportion. So we're going to set up the version of the law of cosines that has little a in it, which means I'm using a squared equal to b squared plus c squared minus those same 2 letters, bc, times the cosine of the included angle A. Sure is. Thank you so much. Imagine I didn't do that. I was totally testing you to see if you were paying attention. And remember, since we're looking for little a and we know big A, that's why I choose that version of the law of cosines. If we fill in what we know and simultaneously square root both sides, we end up with little b, 12.9 squared plus 15.4 squared minus 2 times b times c multiplied by the cosine of big A, which this time I don't have to work hard, is 42.3 degrees. All of that can be thrown into a calculator at one time. We all know how to throw it in a calculator, yes? Can I fast forward? Yeah. Okay. So when I fast forward, I would get A equal to 10.4738 meters. Again, it doesn't tell me how to round, and if you're in the middle of the problem, you might want to leave 4 or 5 decimals since we're probably going to use this value. And we don't want to cut us off too early because it'll change the rounding of previous or like further numbers. Okay, so now that we have A, we now have a pair of letters. So we can go back to what we did last time and we can solve for some of the other things using that pair of letters. I solved mine on my notes in alphabetical order, so we're going to solve for B next and then C last. Is that okay with everybody? So now that I have a pair, I can go back to using the law of sines. This is the sine of A over A. That's the pair I know. I can look for sine of B over B because I don't have big B. So we fill in what we have. This is sine of A. Big A was 42.3 degrees. Little a we just found to be 10.4738. Yes, I want you to use all of those numbers. If you round too early, it will mess up the rounding of the next one we find. So this is going to be equal to the sine of big B over little b, and little b is 12.9. Does this look familiar now? Yeah, because we're looking for big B. We filled in everything we know. We cross multiply, we divide. This will be 10.4738 multiplied by the sine of big B equal to 12.9 times the sine of 42.3 degrees. That's the cross multiply. Then we divide. What am I dividing by here? 10.47. And so sine of B is equal to all of that, 12.9 times the sine of 42.3. I wrote that wrong. LOL. 42.3 degrees divided by 10.4738. Can I put it in my calculator yet?
Yeah.
I've solved for B?
No. Oh, you need to do the inverse.
I need to do the inverse. Remember, B is currently inside of that sine function. So we need to solve for B by doing B equal to the inverse sine, and then I'm going to be lazy for a second, of all of that. Because we need to do the inverse sine of both sides. Now we can throw that in a calculator, and it will give us the angle B. Do y'all remember how to do the inverse sine?
Yep.
Second sine is inverse sine. So we would get that angle B is 55.9872 degrees. Hooray! One more thing missing on this triangle. What am I missing? What angle? Angle C. There are multiple ways we can find angle C. What is the easiest way to find angle C? All of the triangle has to add up to 180. And if we just found our second angle. We were given one, we found one. That's 2 of the 3. That means I can find angle C really easily. I can find angle C by doing 180 degrees minus angle A, which is 42.3 degrees, minus angle B, which we just found to be 55.9872 degrees. And very quickly we see that angle C is 81.7128 degrees. That's the easiest way to find angle C. You could go back and use the law of sines again. You could have solved this whole thing with the law of cosines. Questions, comments, concerns? Once we got to the law of sines, at least, was that part easy?
Yep.
Is your question about the first part?
Do you need to draw a triangle, or is that just for visualization?
It's for visualization purposes. If you aren't given one, though, it's hard to see which rule to use. So no, if you can visualize that triangle in your head and know if you're using the law of sines, cosines, or the angle sum theorem first, go for it. I personally find it easier to see it on a triangle and just verify that I'm using the correct information. Other comments, questions, and concerns? Cool. What happens though if I get an angle or a triangle like this, and it says to solve the triangle if little a is 9.47, little b is 15.9, and little c is 21.1? Do I have any information about any of the angles?
No.
So am I going to have a pair if I don't know anything about the angles? No, this is for sure one where we need to use the law of cosines. Let's start first though by drawing our triangle because it's helpful. So here's my triangle, angle A, angle B, angle C. Literally don't know any of those. But little a is 9.47 feet. Little b is 15.9 feet. And little c is 21.1 feet. No pairs. Can we use the law of sine when there are no pairs? No, so we're going to have to use the law of cosines in some way. I'm going to go in alphabetical order just because I can't help myself with that order. We're going to find angle A first. We have to use the law of cosines to find angle A. So I'm going to use the version of the law of cosines that also uses angle A, which means I'm going to use the a squared equal to b squared plus c squared minus 2 times bc times the cosine of A. I did this because, again, I wanted to find angle A. That's what I'm looking for. Do we know all three side lengths? Yes. So we will be able to fill in everything here and solve for A. But we're going to derive this first before we plug everything in because I want you to see how easy it is to derive them each and every version. Derive means to solve an equation for a different letter. We're going to rearrange this so that it says big A equals instead of little a equals. So I'm trying to get this by itself, which means I need to get this by itself. So how do I get rid of these? Subtract them both to the other side, yes? So it's really going to be a squared minus b squared minus c squared is equal to negative 2bc times the cosine of big A. Did I lose anybody? We moved b squared, c squared to the other side. Trying to get this by itself, which means I have to get this by itself. How do I get rid of the minus 2bc? That would work if there was a subtraction sign right here in between these two terms. But these are all multiplied right now. So I divide. So we're going to divide all of that. This is going to be a squared minus b squared minus c squared divided by negative 2bc equal to the cosine of big A. Remember, we're trying to get the A by itself. Is it currently by itself?
Yeah.
Like by itself, by itself.
You inverse cosine.
You have to move the cosine.
Correct. And how do I get rid of a cosine? Inverse cosine. So really, what I'm going to try to fill in here is the inverse cosine of a squared minus b squared minus c squared, all divided by negative 2bc. I want you to put like a little cloud. Yes.
Could you just skip all that and just do that equation?
Yes. But I wanted to show you why it works and how the pattern comes out. Because if we're finding a different letter, we need to know where the other letters go. Here's what I want you to notice. And maybe put some stars around this as well, because this is going to be very helpful. We're solving for big A. Where is little a? Be more specific. So yes, but also in the beginning. It's the only thing that's positive. This is negative, this is negative, this is negative. So, if I switch this to big B, where would little b go? This would be little b. What would this change to? What would this change to? So you know you can do any of the versions of this as long as you remember the pattern is the side which I'm finding the angle for goes first inside inverse cosine. Yes. Huzzah, we have this isolated for A, and now, again, you could probably fast forward next time you do one of these problems just to here, we're going to throw in everything we need to solve, which means we're going to find the actual A from this problem by doing inverse cosine of little a, which is 9.47 squared, minus little b, which is 15.9 squared, minus little c, 21.1 squared, all divided by negative 2 times b times c. And that's a calculator question. Deriving this with all of the numbers in there would have given us no hint onto how to use this pattern over and over again, which is why we did it with the letters. But once you have it to where there are no variables left and it's a equals, we're going to be able to just throw that in a calculator. Let's practice though, because that's a lot of button pushing. So let's just make sure we got it. I would make sure you use the fancy fraction inside that cosine just to be sure. Very good. So this angle A, the first angle of this triangle, is 24.9546 degrees. Now, there's mathematician's choice at this point, because the law of cosine will work to find the rest of the angles, since we have all of the sides. So you could repeat this process, changing out the letters, finding B, finding C. Or, now that we have A, if I look back at my image, what do I now have? A pair, which means you could go back to the law of sines. We're going to do the law of sines just because that's probably the method you're going to choose, but mathematician's choice, you could 1000% use the law of cosines over and over again for this problem since we know all of the sides. So we're going to use the pair A, big A and little a. We'll find alphabetical order, so we'll find B next. Can't help myself but go alphabetical order. So we plug everything in. You guys are good at this one, so I'm going to go quick because I know you know what's happening here. Ooh. We plug in everything we need. Little a is 9.47 equal to the sine of big B. Oh, we don't know that. Over little b. Little b is 15.9. Cross multiply. Divide. And then inverse sine. Oop, that's lunch. So after lunch, we'll finish this problem up. But go eat. And we'll come back. Didn't turn it off. Okay, so hopefully between going to lunch and coming back, we've evaluated the angle B. What did you guys get?
45.10. Wait, how many digits do you want me to write?
4.
45.101. Wait.
It would round to 0.1020, but yeah. Okay, great. So that's angle B. We are missing just one more piece of information about this triangle. We sure can, because if we have two angles, let's take the easy road out. 1000% you could use law of cosines again to do this, but I don't think you want to. I mean, you might want to. We can find angle C by doing 180 degrees minus angle A, which was 24.9546, minus angle B, which is 45.1020. Yeah, and we'd get that number. So angle C is 109.9435 degrees.
25.
Yes?
No.
It's 3/4.
Show is. I must have saved the number of my calculator and rounded differently. See what I mean by rounding differently? Hopefully your homework always says to round to 2 decimals, which means keep 3 or 4 while you're doing the problem so that by the end you can round appropriately. Are there any major questions about the law of cosines?
That's money go.
No. Well, let's see the law of cosines like isolated. One problem of the law of cosines, like the one we started with. So let's say we're engineering a roof truss, which is the thing that lifts a roof to make it like, you know how roofs kind of look like, they look like little triangles? That thing that does the lifting is called a truss. So if we're engineering a roof truss, let's say we've measured some stuff and we've measured the side lengths of these 3 the beam of the ceiling, and then the roof slant on one side and the roof slant on the other. We want to know the angle for the truss so that we can copy paste that angle for all of different trusses all the way across. Yes. Yes. So if we're trying to find angle B and we were given side, and we were given side, we're going to have to use the law of cosines to do this because we have no information about the angles to have any sort of pair. But if we are finding this truss, which is B, angle B, that means we're going to use the version of the law of cosines that is solved for B, big B. Let's see if we can do this straight off of memory. Don't flip your paper over. If we're trying to do the law of cosines with the version that says big B equals, big B came out of a cosine, so I'm going to do inverse cosine of stuff. What should the stuff be inside that? Let's see if we can remember how this goes. What will go first?
A squared minus B squared minus C squared.
She wouldn't give us a pass, but she said you can call if you want.
The attendance office?
Yeah, but she said they don't give
Miss
us.
Cleary said y'all getting any attention.
No, I did not say you're getting attention.
That's what I texted.
Yeah, so remember, this time we're solving for big B. So what letter should go first? B squared. So we're doing B squared, then minus the other two, so minus A and C. And then in the denominator, which two letters should go there? A and C. Whatever angle you're finding, that side length is used only once, and it's first in the numerator. Which means we can throw all of our numbers in. For us, B would be equal to inverse cosine of B squared, which is 6 squared, minus A squared, that's 11 squared, minus C squared, that's 9 squared. You did, but my point was that it needs to be the letter that you're looking for going first. So if we're looking for big B, little b has to go first. Not the same thing, but I get what you mean. We'll fix it this next time. And so boom. No variables left. Throw it in a calculator. Yes, our calculator should spit out 33.0302 degrees, but this question specifically does tell us how to round. It says to the nearest degree. What's the nearest degree there? 33. So angle B, the angle of the truss here on that side of the roof is 33 degrees. Easy peasy. Well, one more thing. Now that we've seen side, y'all remember in like 7.1, we found the area of some triangles using like an adjusted area formula, like it wasn't 1/2 base times height.
Yeah.
We had a different formula. There's a third formula for area of a triangle. It's called Huron's formula for the area of a triangle. It's used when side is given to you.
Okay.
Side is given to you. That means you have the perimeter of the object. You can add up all of those sides and get the perimeter. But instead, I need something called the semi-perimeter. Semi, like semester, means half. So this is half of the perimeter, semi-perimeter. Or semi-annual cell, means it happens twice each year.
Okay.
So the area, fancy A, of the triangle for Huron's formula is given by the following. The area is the square root of the semi-perimeter times the semi-perimeter minus A times the semi-perimeter minus B times the semi-perimeter minus C. It is a kind of a beast to calculate because it's a lot of typing in the calculator, but it's really simple. You just throw it all in the calculator. Okay, so for example, the distance as the crow flies from Los Angeles to New York is 2,451 miles. From New York to Montreal, that's in Canada, is 331 miles. And from Montreal to Los Angeles is 2,427 miles. What is the area of the triangular region having these three cities as vertices? And we're going to pretend like the Earth is flat.
Okay.
The Earth is curved, by the way. The Earth is not flat. It's not a square. Oh my gosh. All right. So geographically, if I was thinking about this, LA would be on this side of the country. New York City would be on this side of the country. And then Montreal, if you don't know this, is like center-ish of Canada, but mostly center right of Canada, center east. Doesn't matter. Let's say that these are the three cities. Oh, look, they make a triangle. What a coinky dink. It told me in the problem that the distance from LA to New York is 2,451 miles. It told me that the distance from New York to Montreal is 331 miles. And the distance from Montreal to Los Angeles is 2,427. Oof, words are hard. What is the area of the triangular region? Seeing that I want area, and I gave you all of the sides, that should be your indicator that you're using Huron's formula. To do Huron's formula, we need the semi-perimeter, which means we're going to take the perimeter and divide it by 2. So I am doing 2451 plus 331 plus 2427 divided by 2. Since this is dividing by 2, it's either a whole number or a 0.5. So this one is a 0.5. I trust that you know how to add things up, divide by 2. So my semi-perimeter is 2604.5. If I'm actually going to find my area, all I have to do is fill in the formula s square root of s times s minus a times s minus b times s minus c. So here we go. Here's my area. And I'm going to make the longest square root of my life. Not really. And we're going to do the semi-perimeter, 2604.5, multiplied by the semi-perimeter, minus A, multiplied by the semi-perimeter, minus B, multiplied by these, yeah, I know, the semi-perimeter, minus C. And then I have to extend my square root because she wasn't long enough. But look, no solving. It's computation. Definitely not doing this in our head.
No.
Go ahead and throw that in a calculator, and it's a way you can find the area of a triangle when you are given side, side, side. Thanks, Huron's formula.
Yay.
It's supposed to be 401,000?
Should be 402,079.
No decimal at all.
Oh, sorry, I didn't finish writing. 0.5797 square miles. It didn't tell us how to round, so without any information, I always go to 4. This was a gnarly question. I'm pretty sure most of the ones on your homework use numbers like 4, 5, 6 instead of like thousands. But any questions on using that formula? Remember, this is, again, whenever you are given all 3 sides and you're asked for the area, you're going to use Huron's formula. So section 7.1, 7.2, and 7.3 walked us through how to solve triangles using the 2 separate laws of triangles. Your last page for this section is like a nice summary page. So if you flip it over, okay, so since you've proved me wrong, wait, stay right here so I can write this number down. Apparently I typoed when I typed this in, so this should be 401,664.1109.
Yeah.
Is that what y'all got?
Yeah.
Y'all gotta say something when I do crazy things.
Well, Miss, we always do.
True. But that's wild because I straight up, yeah, that's wild.
Wait, Miss, are you gonna like go back and recording?
No, I just recorded over it. Sorry, internet. We're not really writing much in here. We're gonna highlight some stuff maybe. But this law of triangle summary is a great place to have your notes just open at all times when you're doing your homework because it has pretty much every option of triangle you will find. If you are given one side and 2 angles, one side and 2 angles. Well, 2 angles, we can find a third angle real quick.
Yeah.
So we're going to use the angle sum formula. And once we have all of the sides, we can use the law of sines to solve for pretty much everything else we needed. Easy peasy, lemon squeezy. Case 2 was what we did last class. The side-side angle. This is the no cussing rule, the ambiguous case. There may be one triangle, no triangles, or two triangles, so you have to do a little bit of extra work. You're going to start off with the law of sines. Once you have the law of sines finished, you would have another angle, and we can go back to that angle sum formula. The only problem is, we find the remaining side using the law of sines. The only problem is, if two triangles exist, we're going to have to repeat steps 2 and 3. The way we check if two triangles exist is the following. We see if there's a second angle B, or whatever angle you found second, we do 180 degrees minus the angle you found, and check and see if the angle given and the angle you found as an option are less than 180. And if they are, then there's a second triangle. And so we repeat. I get those ones are hard. You need to know how to do one by next class, if you catch my drift.
Oh, that one?
Mm-hmm.
What?
This case.
Really?
The third case was what we started learning off today, is two sides and their included angle. We started off by using what was called the law of cosines to find the missing side. Once we had that missing side, we then had a pair of terms, so we could go back to using the law of sines and end off nice and cute with the angle sum formula. However, the other option we saw today was when you were given all three sides and no angles whatsoever. So we're going to find one of the angles. The book suggests finding the largest angle first, so it's probably going to have you do that first. But you can find any of the angles first using the law of cosines. But before you highlight that, hopefully you didn't already highlight that, I want you actually to cross this out. Because we are not finding a side length here. What are we looking for?
Angle?
An angle. So instead of writing our equations that way, we're going to write the version where the angle is isolated, which is where we do the inverse cosine of that same letter's side length minus the other 2 divided by -2 times the other 2, all within an inverse cosine. Obviously, the letters will switch around, but this is the version of the law of sines that we would rather use. We derived this formula for ourselves in the notes. Okay, it is literally the ones that are written there. Those are not wrong. They're just not useful because we're going to have to solve for an angle. But once we have one of the angles, we then have a pair. So we can go back to the law of the law of sines. Or yeah, you can use the law of cosines if you wanted, but mathematician's choice there. And then we end with the cute angle sum formula. So we have a lot of variety of triangles you're given. We do need to start to memorize what we're going to use for each of them so that you can do this without really looking at very much notes, or you write really good notes to yourself on the front page.
Or just using it.
Yeah. But these are the things I'm going to have you do in section 7.1 through 7.3. That is also what your quiz is over next class. And if I remember correctly, there's 4 questions on it because I know y'all are going to ask me that question.
Yeah.
Okay, it's a variety of things from 7.1 to 7.3, including area, which is not on this page, but this is the law of triangles summary. Questions, comments, concerns?